Hey everyone, and welcome to The Explainer. I'll be your lead database architect today, and I am absolutely thrilled to walk you through the architectural blueprints of modern data. Now, before we get too deep, there is a core engineering philosophy we need to establish right out of the gate. There is no longer a one-size-fits-all database to build successful digital products today. The landscape has totally evolved. Choosing the right tool is literally the difference between a system that scales beautifully and one that completely crashes under pressure. Okay, let's dive into this. Here's our blueprint for today. We're going to cover beyond one-size-fits-all, taming data chaos with NoSQL, warehouses, the corporate brain, mining for hidden insights, and finally, specialized tools for unique jobs. Let's get to it. I want you to start by asking yourself a pretty critical question. Is your database actually holding your whole project back? Imagine the absolute disaster of trying to force modern, highly unstructured, rapidly changing mobile app data into a rigid, old-school relational spreadsheet. It's like trying to fit a square peg into a round hole, right? But the peg keeps changing its shape. It simply doesn't work for today's massive scale. All right, jumping right into our first zone, beyond one size fits all. As an architect, when someone hands me a brand new business problem, the very first question I ask is this. Does this data structure require strict rigidity, or does it demand dynamic flexibility? That's the fundamental choice. On one side, we've got traditional relational databases. They enforce a really static, rigid schema, they scale vertically, basically by buying a bigger, beefier server, and they strictly enforce ACID rules to guarantee absolute data consistency. But on the flip side, we have NoSQL databases. These give us dynamic schemas, where records can just change on the fly. They scale horizontally across clusters of much cheaper commodity servers, and they operate on what we call the base model, basically available, soft state, eventual consistency. Basically, you're trading those strict rules for incredible speed and continuous uptime. Moving into section 2, let's talk about taming data chaos with NoSQL. Now, what's really interesting about this slide is how we pit two NoSQL giants against each other because they solve completely different problems. First, we have MongoDB. It's a document-oriented database storing massive speeds, making it the absolute ultimate choice for high-velocity IoT sensor data and massive log streaming. Okay, shifting gears to section 3, warehouses, the corporate brain. So, we're shifting our focus from the absolute chaos of live application data over to corporate history. All of our rapid, messy transactional data has to eventually be unified into a single, clean source of truth, right? Otherwise, executives can't make informed decisions. We do this through the cradle-to-grave data lifecycle known as the ETL pipeline. First up, we extract the whole shebang. Finally, we load it into a central, read-only warehouse repository. This is exactly how messy, flat logs transform into clean, time-variant corporate history. Right, so once the data is actually loaded, how do we organize it so we can analyze it really fast? Architects design what's called a star schema. Imagine a central fact table packed full of quantitative metrics, like total revenue or units sold, sitting right in the middle. Then we surround it radially with denormalized dimension tables, holding all the descriptive attributes, like store locations or product categories. This specific layout is explicitly designed to accelerate complex, read-heavy analytical queries over millions of rows, totally avoiding the slowdowns that would crash our active production databases. Which brings us perfectly to section 4, mining for hidden insights. Look, building the warehouse is really only half the battle. Now we actively have to extract valuable hidden structures from it. But before we run a single algorithm, we have to confront a massive engineering challenge. Garbage in, garbage out. You've probably heard it, but man, is it true. In the real world, corporate data is incredibly noisy and incomplete. Even the most advanced, state-of-the-art predictive machine learning models will completely fail if the underlying data they're fed is corrupted or noisy. To prevent that absolute disaster, we rely on the Knowledge Discovery in Databases, or KDD process. Notice here that actual data mining is just one mathematical step inside a much larger pipeline. We've got to clean and integrate the data, select and transform the right features, then run our mining algorithms, and then crucially, evaluate those patterns to ensure they aren't just accidental random correlations before we present them as actionable dashboards. And this brilliantly illustrates why all that prep work matters. The real-world applications are just... Okay, let's hit our final section today, specialized tools for unique jobs.
We are now going to dive into some hyper-specialized tools that are designed for modern edge cases, stuff that standard databases simply cannot handle. First up is the active database. Traditional databases are, well, they're completely passive. They just sit there and wait for an external application to query them. But an active database, it uses an event condition action, or ECA architecture. It actually monitors its own internal state and really brings the database to life.
So the crucial point is what this looks like in practice. Imagine an e-commerce warehouse. The event is a stock update. The condition evaluates if the stock has dropped below a specific minimum threshold. If that's true, the action automatically generates a vendor purchase order directly on the database server itself. No manual application intervention required whatsoever. Pretty incredible, right? Next up, we have spatial databases. Now, standard databases fail spectacularly at multidimensional coordinates because their indexes are strictly one-dimensional. Spatial databases fix this whole mess by using structures like R-trees. They group multidimensional objects, points, lines, polygons, into bounding boxes. This lets us do instant filtering across both X and Y axes simultaneously. Think about it. Every single time you open up a ride-sharing app and it instantly finds all available drivers within a 2-kilometer radius, you are triggering a spatial database query right there. They are the invisible engines powering everything from fleet logistics routing to environmental conservation mapping. Then we've got the mobile database. Think about smartphones or embedded field hardware that experience really intermittent network connectivity and high latency. They just can't rely on a constant connection to the cloud. So mobile databases run a lightweight footprint locally. This allows read and write operations directly on the device itself, and then they sync up with the synchronization gateway the second the network is restored. So what this means in the real world is that remote field workers, or maybe equipment deep out in a cellular dead zone, retain full, seamless database functionality. They can modify records completely offline, and the system's conflict resolution protocols handle the data merge flawlessly once they step back into Wi-Fi range. All right, finally, let's check out the deductive database. Standard databases only spit out exactly what you typed into them, but a deductive database, it combines relational tables, which we call the extensional database, with a declarative logical rule engine called the intensional database. It uses an inference engine to deduce completely new facts on the fly based on rules you provide. Let's walk through a really brilliant example of this. If you only store raw facts, like Anil is the parent of Sunil, and Sunil is the parent of Amit, a deductive database can use a very simple logic rule to automatically infer that Anil is the grandparent of Amit. It evaluated those base facts and produced a completely new, unrecorded conclusion without us ever having to actually write that specific data to the disk. And that pretty much wraps up our architectural tour. From scaling out massively with Cassandra to inferring brand new logic with deductive engines, choosing the right architectural tool absolutely unlocks unlimited possibilities. So I'll leave you with this final provocative thought. Now that you know exactly what's sitting in the toolkit, what will your data build tomorrow? Thanks so much for joining me on this explainer, and keep exploring.